So I did upload the video from Tuesday this morning. I just forgot to upload that. So are there any direct questions about any of this? Again, the best way to prepare for the test next Tuesday, I believe, is to go through the questions, these quizzes that look like homework, but they're not really homework, they're just practice for the test. So I'll just keep going over these, but nothing specific, nothing direct. How ready for the test do you feel? Okay. Well, if you're not, be sure and be busy on it between now and Tuesday. I teach labs most of today and most of tomorrow, so probably if you want to meet with me, probably have to do it Monday, because I barely have any time. I have some time after class right now. First lab isn't until 1 p.m. Oh, yeah, I still have to do 11:52 makeup, so, okay. I want to mention this too. Let me back up. I just forgot to open this one. It's in the chapter 3 one, vocabulary and conceptual. I'll go over some of that today. But I think it was Tuesday morning that I realized I hadn't opened that. So just in case you didn't know it was there. I think this is about where we are going over things. So, this first question, which of these statements is false? So the number of protons is equal to the number of electrons in an atom. That's true for the neutral atom. I always say the neutral atom on the test. Protons and electrons don't always equal each other because sometimes an atom can lose electrons or gain electrons to become ions, which is obvious once you get to the next chapter, but that should say for the neutral atom. I think vocabulary-wise, we use the word atom when it's neutral, and when it's charged, we call it an ion. So maybe that statement's fine, but I like to say neutral atom just to be clear. Each element on the periodic table has a unique atomic number. Is that true? That is true. And that's what these integers are on the periodic table. Electrons are found in orbitals residing outside the nucleus. That's true. The mass number is the sum of the number of protons and neutrons in an atom. True. Most of the masses are found outside the nucleus. So textbooks love to say this, and it is true. The protons and neutrons are where most of the weight come from, and those are in the nucleus. But most of the space of an atom is taken up by the electrons. So the mass is concentrated in the nucleus, but the size of an atom, the volume of an atom, mostly comes from the orbitals of the electrons. Aren't one of these supposed to be false? Yeah. So, do you know how to decide which element is chemically similar to lithium? Lithium is right here.
Same group.
Yeah, same group, which is another way of saying that. What's another way of saying group? Column, yeah. So columns are groups, periods are the rows. So anything in this row is going to be chemically similar. And chemically similar, that's related to the fact that everything in that first group will all become a +1 ion. That's really what's so similar about them. And of course, that means they behave similarly in ionic compounds. So what else is sulfur, magnesium? Which one is it?
Potassium.
Potassium, right? Okay. All right, which statement describing atoms is false? Number of protons in an atom, is this the same as the other one? No, it's different. The number of protons in an atom is referred to as the atomic number of the atom. Is that true? That is true. Total number of protons, neutrons, and electrons in an atom is referred to as the mass number of the atom. Is that true? It's not true. What is true about the mass number?
It's just the protons and
Protons and neutrons is basically the stuff in the nucleus. So I guess the rest of these have to be true. Protons and neutrons are in the nucleus. Electrons are located in space outside the nucleus, also called the electron cloud. The number of protons is equal to the number of electrons. That's true for the neutral atom. So which statements concerning the elements fluorine, chlorine, bromine, iodine? So that's these. What are these called? They're called the halogens. Okay, they're all halogens. All the elements have the same valence shell. Is that true? Not true. That's the one that's incorrect. Fluorine's valence shell, because it's in the second row, is 2. Chlorine is in the third row, so that's the third shell. I'll draw some electron configurations in a little bit. But the valence shell goes up a number every time you go down. So second shell, third shell, fourth shell, fifth shell. All these elements have the same number of valence electrons. That's what's true. They do have the same number of valence electrons. The quick way to see how many they have is, for instance, for chlorine, you point at chlorine and you go 1, 2, 3, 4, 5, 6, 7. So all of these do have 7 electrons in the valence shell. It's just their valence shells are different. Located in the same group of the periodic table, yes. Okay, strontium is here and barium is here. And do they have the same chemical properties? They do, because they're in the same group. Electron configurations. I guess I'll draw some electron configurations. So aluminum. I could look at the periodic table to get started on this. Boy, I always tell y'all to do this. What am I gonna do? 1, 1, 3, 1, 3, 5. Start that with electron configurations. Just roll off the page. 1, 1, 3, 1, 3, 5. But just remember, it's 1, 1, 3, 1, 3, 5. But just remember, I always stick something else here. What is it?
just numbers.
It's 1 more 1. That breaks that neat pattern, 1, 1, 3, 1, 3, 5. And then, if you can do that, that's quick. And then all these singles are S's, including this one weird one that breaks the pattern. The 3 across are P's. Those are just called P orbitals. What are these called? D orbitals. It's S, P, D, F. I'm not going to give you any that go as far as F, but F is 7. So it goes 1, 1, 3, 1, 3, 5. And then this one starts 1, 3, 5, 7. And the numbers I'll put here, you just start down here and you go 1, 2, 3, and this weird one is 4S. And since I've already started 2, once I get to here, there's 2 here. 3S, 3P, got 1, 1s, 1, 3, this is the number 2, n equals 2 level. And the 1, 3, 5 are all 3. The third row of the periodic table. If you look at the third row here, so here is the 3p. That's these getting filled. These 6 spots, 1, 2, 3, 4, 5, 6. When we're filling these, and then when you drop down, now you're at the 1, 2, 3, 4. That's the 4s, the weird one, and that's when the d orbitals start. And I told y'all that the highest ones I'll do are up to about here. Things get a little weird after that. But this way I fill the orbitals will work for anything you guys will get. That's n equals 3, and n equals 4 is where they start to bunch up. So the first shell, this is the second shell, these are called subshells. So that's a subshell, that's a subshell. Okay, for aluminum, I'm about to do the electron configuration of aluminum. What do I want from here? Certainly I'm gonna look at aluminum, but what am I gonna look at?
The atomic number.
Yep, the atomic number. Technically, that is the number of protons, but we're doing electron configurations of neutral atoms, so of course it's gonna be that many electrons. So I'm going to take that number 13 and start this process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You can see that aluminum fills the 3s, which is this, and then it gets one more, which is here. So that's the electron configuration of aluminum. And that's just one way to represent it. And like I said, I seem to be the only one that still does it this way, but I think that's so simple, the Christmas tree. The other ways you can write this, which is the way this question does it, is go 1s with 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 3s with 2, 3p now with only 1. That's another way to do the electron configuration. If I do it the other way, where I sort of do the core, which one of these am I going to write in brackets? So if you look at aluminum, and you back up all the way to here, aluminum's down here, it's neon. If I did the electron configuration, that would be it for neon. So in some sense, that equals that, the electron configuration of neon. And then, so that's another way. Now there's 3 ways. And I might do this on the test where I go 1s, 2s, 3s, 3p, the 4s definitely comes next. Of course, I won't be using those. And then you could do 5 boxes across. I've just run out of room for the 3d. But I'm not going to need the 4s. I don't even have to draw that because I'm going to stop there. But there's another way to represent exactly the same thing. It's just sort of four different ways to encode the same thing. This is the best way to picture it, I think. This also refers to, if the nucleus were down here, and you pictured a circle around the nucleus that represents the 1s, and then the 2s. So that's what these levels indicate. The further up means the further away from the nucleus. It also means higher energy. So the energy in the electrons here are higher than the energy of the electrons here. And these are higher than the energy of the electrons here. This is the lowest state. I mentioned also that your book likes to call it the ground state configuration. It is possible, we don't really talk about spectroscopy in this class, but one photon of light can come in, if it's got the right amount of energy, you can hit this electron and pop it up here, and then that would be an excited state. But just in case you come across the word ground state is exactly what I draw for configurations. Is it B here? S2, 3P1, yeah. This one has to be B. What else we got? Can you tell which one this is? Just by looking at it. The 1s is full, the 2s is full, the 2p is full, here's the 2p. 3s is full, that's here. And then you've got the 3p is full because there's 6 of them. It's argon. It's this. You see? Okay. The maximum number of electrons that can occupy the N=3 shell. So it's basically asking you how many electrons can fit. It also includes these. So I'm color coding the N=3 level. And how many electrons can fit in there? It's 2 per line.
18.
2, 4, 6, 8, 10, 12, 14, 16, 18.
Also for question 1, could it also be F since that's for all that apply?
Oh yes, very good. I'm not sure how that's gonna grade. But yeah, you're right, this is just one of those alternate ways of doing it. Okay. I'll see how this grades. 18. You can do this. You can do it the way I taught you to go 1, 1, 3, 1, 3, 5, and make sure you put the 4s where it goes. But that really is just following the periodic table. I just told you to memorize that because it's quick. 1, 1, 3, 1, 3, 5. And if you can remember the 4s goes in there. So you can continue to build this up to know what comes next, looking at the periodic table. I'm not sure which one of those is right, but let me write them out. I think I want to keep this. Just leave those blue. So you've got the 1s, 2s, the 2p, 3s, 3p, 4s, 3d, and then what comes next? This is the 3d transition phase. So this is the p block. So p is going to be next. It's the 4p, and you can just build up from there. But 4p next is 5s, or 1, 2, 3, 4p. Next is the 5s, and then the 4d. So you could use a periodic table to continue to build. don't know what's up with the weird spaces they put in here. It says 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P. That was wrong. 4S. This one, 1S, 2S, 2P, 3S, 3P, 4S, 3D, and then 4P. Yep. That one is correct, assuming none of the others are correct. But you could do the whole periodic table now, just continuing that pattern and looking at the periodic table. So which one would this be? 1S2, 2S2, 2P6. So this is full all the way up to neon, 2P6, 3S2, this is the 3S, so I guess that's magnesium. So fluorine is gonna, here's fluorine right here. So you've got 1S, 2S, and then 2P6. 1S, 2S, 2P3, 2P5, 2, 3, 4, 5. Yeah, it's 5, 2P5. Is that right? Is that the right one? It's not 2P3. Doesn't go up to 3. A noble gas is going to end with something P, so that doesn't. 3P6, but I guess we better check all of them. S2, S2, 2P6, 3S2, 3P6. I think it's got to be that one. But I was looking for P6 from all the answers first, because you have to have the P orbitals full. Noble gas notation. So here's neon, and then next we have 3S, this is full, and then we have 3P2, so we're out to here. So this one's going to be silicon. You follow this? Electron configurations look very abstract, but there is something very easy about these. So calcium is here. 2, 3, 4. So we're looking for 4S2 at the end. And none of them are there, so it's this answer. See what I mean? I was just looking for 4S2 at the end, and none of them had that, so none of them could be correct. This is magnesium as well. 1S2, 2S2, 2P6. So 1, 2, 3, and it's got a 2 in the S, so that one's going to be magnesium. So 1S, 2S, and then 1, 2, 3, 4. 1, 2, 3, 4. So that one's got to be oxygen. I just put a lot of examples here, but they're all just kind of the same.
So on that last one, if you go back, why is there ozone mode, I think?
This one?
The oxygen one. So there's one arrow in each of the last two boxes. So what does that mean? Like, since there's not two?
One arrow in these two.
Yeah, like why is there not two in the one in the middle one?
Every time I do this, when I fill this, so oxygen is 8. So if I did it this way, I took the number 8, I would go 1, 2, 3, 4, 5, 6, 7, and then you come back and start pairing.
Oh, right. When orbitals are equal in energy, one electron is added to each orbital. Okay, the ones that are adjacent to each other, like these three, those are equal in energy. So it's distance from the nucleus
but you can also think of it as energy, and any of them that are all on the same level, all have the same energy. So these electrons have the same energy. When orbitals are equal energy, one electron is added to each orbital until the orbitals are half filled. Before, that's true. You follow that? Every time I go across and then I come back and pair them. I haven't said much about this. When two electrons occupy the same orbital, they have paired spins, that is, the spins are opposite in direction. That's what those kind of half arrows are. Electrons have a magnetic moment, so it's just like if you play with magnets, you got a north and a south. So you have to draw the electrons opposite to each other. Six A, 1, 2, 3, 4, 5, 6. So that's 6A. All right, this isn't true. If it said NS2 NP4, that would be right, right? 1, 2, 3, 4, 5, 6. I don't tend to use that questions about this different coding. Just numbering 1, 2, 3, 4, 5, 6, the numbers that you have on your periodic table. I'm fine with that. I think it's kind of anachronistic. All right, which of these have the largest radius? It's really a matter of finding them on the periodic table. So what's this periodic trend size if going across one row? It gets smaller as you go across. As you go down a row, they get bigger, but as you go from left to right, they actually get smaller. Those two rules are all you need to know to answer questions like this, but I guess we have to find all of these. There's potassium. Gallium is down here. Bromine is here. Rubidium, RB, is down here. Sodium is up here. So which one has the largest radius here? We're comparing these three and then some along here. RB is the largest one here. It's the one that's furthest down the road. So it's this one. The smallest one here would be sodium. And when it comes to potassium and gallium and bromine, bromine's the smallest one among those three. And potassium's the largest one. Because these get smaller as you go across. And these get bigger as you go down. Here's sulfur and here's oxygen. Sulfur atom has a larger atomic radius than oxygen. Sulfur contains more electrons, sulfur contains more protons, sulfur contains more neutrons. The larger number of protons, and oxygen pulls the electrons closer. The explanation for why they get bigger as you go down is more electrons. The answer for why they get smaller as you go left to right is more protons in the nucleus. Because you get another proton every time you move to the right. That means one more positive charge. And then the more positive charges in the nucleus pulls the electrons in a little bit. So they get smaller and smaller and smaller as you go across. And it's not until you start that next energy level that it jumps big again. And then it gets smaller and smaller and smaller as it goes across. So I expect that's what they're getting at here. When it comes to comparing oxygen and sulfur, sulfur has more electrons than oxygen, that's why. No, I guess this is the better answer. Both are true, but the valence shell of sulfur is farther away from the nucleus than the valence shell of oxygen. bromine is smaller than potassium. So here's potassium, and here's bromine over here. So is bromine smaller than potassium? Iodine atom is larger than both krypton and tellurium. So krypton is here, and tellurium is down. Where is tellurium? Te. There it is, down. So there's krypton, there's tellurium. Tellurium. Iodine atom is larger. An iodine atom is larger than both a krypton atom and a tellurium atom. So there's bromine, there's iodine, there's tellurium. So is iodine bigger than bromine and tellurium? It's not. Iodine is larger than bromine, but it's smaller than tellurium. Does that make sense based on those rules? So look at the answers. I think they're really playing games with the concepts there, but anyway. I won't get that weird on the test. Okay, ionic compounds. We covered this a little bit Tuesday just because people had questions. So what would you call this? SN is 10. It is right here. So what are you gonna call that? Yep, that has to have 4 Roman numeral in the parentheses because it's down here. Any transition metals and any metals that are down below that jagged line that represents the metalloids, those have to have the parentheses. For some reason, textbooks treat a few of them as exceptions, but I treat them all the same because it's not really true. So anything in the transition metals and anything down here have to have the parentheses to tell you what the charge is because they have more than one charge. It's true of these down here too, but I just pretty much ignore these when I teach this class because we never use those. They're so rare. These are the F orbitals down here. Ionic bonds form between a metal on the left side of the periodic table and a non-metal from the right side. It's not the best way to put it, but that's the answer to the question. It's really the top right corner. Non-metals are the top right corner, ignoring the noble gases and adding hydrogen to it. And the metals are everything else that are not noble gases. How would you name this? That's Ki, there's potassium right there. Iodine is over here. What would you call that? Potassium iodide. Did you say iodide? Yeah. No parentheses is needed because the charge on potassium is always going to be +1. Which pair of elements will form an ionic compound? How do you decide that? Metal and a non-metal. So you're looking for a pair there that's a metal and a non-metal. Sulfur and oxygen are both non-metals. Those will make a molecule. Copper and iron, those are both metals. That'll make a metallic compound. Iron and chlorine is going to be the answer here. Bromine and oxygen, those are both non-metals. Magnesium and lead, those are both metals. So iron and chlorine, there's iron in the transition metals. Chlorine is up here. If I ask you what compound can be made, name the compound that's made between iron and chlorine, you couldn't answer it because I'm not telling you what the charge is on iron. You'd have to know that somehow to know what the formula is and to know what the name is. Because iron can have more than one charge and it's not specified here. potassium and bromine together, what's it called? Potassium is here. Oh, that wants the formula. It's KBr because K is +1 and Br is -1, so you only need one of each. So the formula is just KBr, you don't need any subscripts. And the name of it, potassium bromide. All right, this one, it is actually telling you the charge on copper. Cu is copper, Cl is chlorine. Do you see how you know the charge on copper? Just by looking at it? They've given you the formula. That's right. The chlorine is definitely -1. There's no variable charge there. And since there's only one chlorine there, there's a total of -1 charge. And since there's only one copper, all of that -1 charge has to be counteracted by that one copper. So that's necessarily copper charged 1 because the formula doesn't have any subscripts. You see that? So copper 1 chloride. So you've got magnesium and you've got fluorine. What's the name of this? What is it? Magnesium is here. It's just magnesium fluoride. Because that magnesium is not in the transition metals or down below the metalloids. Magnesium always has the same charge, so you don't need to tell the charge in the name. So that's just magnesium fluoride. It's not magnesium difluoride, it's not magnesium 2-fluoride, it's just magnesium fluoride. I probably won't ask you this on the test because I'm giving you those. I'm going to give you on the test. It's messing me up. Where are we? Yes. Spring 2025. So, I'm gonna give you these on the test. Crash, yeah, crashed. So I'm gonna give you those on the test. And these. So you can just find it in the list. That one's sulfate. I don't know why that came up though. Polyatomic ions, that's it. So that one's sulfate ion. What is sulfide ion? It's just sulfur. Sulfur with IDE on it. But there is such thing as sulfite and sulfate and bisulfate, but they're all on this list here. Sulfate, sulfite, bisulfate, bisulfite. But sulfide is just S2 negative. Okay, what is the chemical formula for 10,4-cyanide? Cn is the cyanide ion, so that's a polyatomic ion. Which one of these is the correct formula? Oh, you can look here and find cyanide. You get the name, you get the formula, and the charge. So cyanide, Cn, is a negative charge. One negative. So 10,4 cyanide, what is this 4 telling you? Hmm? The charge on 10. So they're specifying that 10, which is here, has a charge 4. Cyanide has a -1 charge. So what's the formula? What is it? It has to be this one with the parentheses. This extra space, I should go back and edit all these. These I downloaded from McGraw-Hill. But SNCN4 would say that there are 4 nitrogens. That makes more sense when we get to molecules in chapter 4. Cyanide is CN negative, 10 is SN, and that 4 tells you it's 4 plus. So you're gonna need 4 of these to balance this, so SN. If I wrote it as SN, I'm saying that there are 4 nitrogens and only 1 carbon. This really represents SN 4 plus. There's 4 CNs there. So really there's 4 nitrogens and 4 carbons. It's not that there's no carbon and 4 nitrogens. So you have to use the parentheses for these. NH4, so those aren't on there. I told y'all the only ones to memorize, and NH4 is probably the most important one. So just memorize this one, NH4. This list, notice everything here is negative. Nearly every polyatomic ion is negative. There's only a small handful of positive ones. But that doesn't tend to make ionic compounds. There's metallic compounds that I told you we don't talk much about. Ionic compounds, metal and non-metal. And then molecules, covalent compounds, non-metal, non-metal. And then there is a 4th type of compound that we won't study called coordinate covalent, and those tend to show up in metals. I think that comes up like once in math later in the semester, but we don't even point out that they're coordinate covalent. So that's the only one to memorize. So where was I? Here. So this is ammonium, and the SO4 is here, sulfate. So the formula is correct. There's 2 NH4s for any one SO4, because SO4 is 2 negative. So I guess the answer is obvious now, right? I made that one seem hard. If you know that NH4 is ammonium and SO4 is 2 negative sulfate, then you can easily pick out ammonium sulfate. Okay, the correct name for Ag2O. Ag is silver. It's right here.
only one above it, liquid ammonia. Why is it ammonia, not ammonium?
Did I say ammonia?
Yeah.
Ammonium sulfate, I was wrong. It's ammonium sulfate. Just so you know, ammonia is that's a molecule, which is, it hadn't come up yet. This is a molecule too, it just happens to be charged, so. We'll cover molecules in the next chapter. So yeah, that's ammonium sulfate, my bad. Ag2O. And Ag is down here. Nobody?
Would it be silver one?
Yes. It's silver one. What is it? Oxide. Ag2O. What's the charge on oxygen? And you only have one of them. And you have, so the total negative charge is -2. Therefore, the total positive charge has to be +2, but you have to split it among two AGs. So both of these are +1. And that's where we're getting that from. Silver 1 oxide. You guys okay with that?
You have to put back those parentheses down since silver
Yep.
can have.
Silver's down here, so you have to put the parentheses. And to figure out what the charge is that goes in there, you look at what's here and you have to balance it. And since there's two of them, you have to split it into two. Silver 1 oxide. Au is gold, it's down here. Silver, there's gold. Au, that's I3. Here's iodine over here. So you need the parentheses, right? There's only one gold there. It's AuI3. Hmm?
The dark one.
It is the third one. It's gold 3 iodide. 3 is not because there's, this 3 is not referencing the 3 on the iodine. It's referencing the charge on the gold that's there. And since there's only one, does it make sense? That balances the charge. The 2 in the name lead-2 acetate specifically indicates that there are 2 lead ions present in the compound. Is that true or not true? It's not true. It references the charge on the lead, not how many are there. That's false. HPO4. Again, when you look at this, you can isolate the metal, and then the rest of that is going to be the polyatomic ion. So HPO4 is the polyatomic ion. We just look here. HPO4, it's hydrogen phosphate. So this is calcium, hydrogen phosphate. CaPO4 without the H would be calcium phosphate. This is calcium hydrogen phosphate. So that's false. You guys okay with that? This was potassium bromide, KBr. This is iron and chlorine. metals on the right. Oh. What's the other name for this one? I might put one question like this on the test, but I'm giving you these as well. I consider this is a different naming system. And it's kind of antiquated, but you still see it a lot in labs. That was, what was it?
It was tin for fluoride.
Fluoride. Which was SN. That was the formula. The other name for this, is that even in there?
No, it was fluoride,
It was fluoride.
yes.
10, there it is. When 10 is 4, you can also, instead of putting 10 4, stannic refers to 10 when it's plus 4. It was what, bromide?
Fluoride.
So you could also call this stannic fluoride. When you use that naming system, you don't need the parentheses because stannic is referring to the plus 4 form of 10. But since I give you that chart, you can do those types of naming. But that's kind of antiquated too. But when I looked at the answers, if I don't specify, you can do either naming system. It didn't specify, did it? Formula for stannic fluoride. I misspelled it too. You can tell I don't like that naming system. I like systematic stuff. They tell you science has really systematic naming and concepts. And the truth is, it really does. It really does. They use antiquated things, and I don't know. It's kind of messy. Naming ion compound. Do we do all that? Naming ions. This section is kind of. Since I give you all the names of the polyatomic ions, the rest of this is just about when you use "-ide" at the end of nonmetals and stuff. For polyatomic ions with 8 and "-ite" suffixes, such as sulfate and sulfide, the ion with the 8 ending has blank oxygen atoms. You could just look here. I don't think I've said this since I'm just giving you this chart, but it is true that sulfate has 4 oxygens and sulfite has 3. So the difference between 8 and "-ite is the number of oxygens there. There's another one, nitrate and nitrite the same way. 8 has 3 and "-ite has 2. But I probably won't ask that on the test. But there is a little bit of systematic naming and stuff like this. This is a really complicated ionic compound. I won't bring something up like that on the test. But can you tell what the 2 polyatomic ions are? This is a big polyatomic ion, or I shouldn't say big because it's a crystal, no matter how you look at it. But the formula for this has actually 10 calciums for the positive. And then you also have PO4 and OH. So this one's looking for PO4 phosphate. OH is hydroxide. So you could just look up a question like that on that sheet, which is probably why I won't ask it. Let's get this sized. So that's phosphate, and this is hydroxide, and that's what it's looking for here. The name of an anion usually ends in "ide" if it is derived from a single atom, or "ate" or "ite" if it's polyatomic. That's true. This is nitrite if you look it up. Sodium nitrate, sodium nitrite are two acceptable names for the same compound. They're not the same. Nitrite and nitrate are different. Sulfite ion contains more oxygens. False. But all of those you can answer just by looking at that sheet I gave you. So that's why I'm not harping on it. What I'm really saying is I probably wouldn't give questions that simple on a test where you just look it up on the sheet. So do look at those questions, but I'm probably not going to ask them on the test. So naming ions. Formulas for ionic compounds. Class building. Iron 3 bicarbonate. You can write the formula if you knew bicarbonate without looking anywhere, but since I'm giving you this, where's bicarbonate? So HCO3 negative. And was it iron 3? So you look up bicarbonate, and then it says iron 3. So what's the formula going to be? You basically just need 3 of these. So that's the formula. Can you tell me which of these is not an ionic compound? So you're looking for metals and non-metals. CBr4, yeah. So carbon and bromine are both non-metals. So non-metals, if it's only non-metals, it's a covalent compound, which is chapter 4. The rest of these are metal, non-metal, metal and polyatomic ion, metal and non-metal. So that's going to be the answer here. That's not an ionic compound because it's a non-metal and a non-metal. No metals, which is not a covalent compound. Br is a non-metal. Nitrogen and oxygen are both non-metals. Nitrogen and hydrogen are both non-metals. Here we have sodium and a polyatomic ion. That's the one that's not covalent. That's the same question that was on the other one, right? Potassium and bromine. Okay, lithium oxide. Lithium is here. Oxygen is here. It's the third one. Lithium is +1 and oxygen is 2 negative. So you've got to have 2 lithiums to balance the -2. So it's Li2O. So magnesium and oxygen. Magnesium is right here, oxygen is here.
Just MgO.
Yep, it's just MgO. Magnesium is 2+, oxygen is 2 negative, so just 1 to 1. And like I've said before, for some reason in chemistry we don't write the ones. But MgO means 1 magnesium and 1 oxygen. Okay. What is the formula when aluminum and sulfur combine? So aluminum is here, sulfur is here. What's the charge on aluminum? It's 3 plus. First column is +1, second column is +2, and then the only other one is aluminum +3. They always have the same charge. Every other metal has variable charge. So aluminum is 3 plus, and was it sulfur?
Yes.
Sulfur has a charge of 2 minus or -2. Another weird thing chemists do, we put the charge on the other side of the number. So how are you gonna make these balance? It's when there's 3 and 2, or if it's 2 and 3, it's only really rare when you tend to get in introductory chemistry classes. But you have to sort of think least common multiple. So you're gonna have to have more than one. It's when there's only one of them that it's easy. But when they're like this, there's gonna be more than one aluminum and more than one sulfur. Do you remember what you do here?
To like make it both equal 6.
Yeah. Just think least common multiple is 6, 2 times 3 is 6. You're gonna need 3 of these and 2 of these. That'll do it. That'll give you a +6 and a -6. Make sense? I think it's the only one that's tricky. There are larger, the example, like, some of these in here can have like a +5, but you don't get any questions like that in the chapter, so I won't do it like that. What did I say? Al2S3. Calcium selenide, so calcium is here, selenium is here. What's the charge on calcium? And what's the charge on selenium? So it's just 1 to 1. So this, as weird as it looks, is the formula for calcium selenide. What is the charge on the iron compound, Fe2O3? Charge on oxygen is 2, and there's 3 of them. So it's kind of like this, but backwards. You're being given the formula. What is it? I've already forgotten. Fe2O3. And it's saying, what is the charge on iron? So you think like this, what's the charge on oxygen? 2 minus, and there's 3 of them. They add up to -6, or 6 negative. There's 2 irons, and you have to have a +6 out of them, so you split that among the 2 irons. So it's just backwards from the one I just did. You're reasoning the other way around. So these have to be 3 plus. So the charge on iron here is 3 plus. Or +3. What's the charge on nickel here? Nickel is down here. Somewhere, there's nickel. Chlorine is here, so what's the charge on the nickel? What is it? 2, yes, +2. Okay, which Roman numeral correctly completes the name of chromium oxide? So what's the charge on oxygen? 2. And there's only 1 of each here, so what's the charge on chromium? +2. So you have to have a chromium 2 oxide. So CH3CO2 is the acetate ion. CH3CO2, it's one negative. So formula for zinc acetate. Zinc is down here. If I ask you this, they're calling it zinc acetate without the parentheses because they're pretending there's only ever one charge on zinc, which is not true. That's one of those things that just bugs me. But they didn't use the parentheses because apparently books try to pretend these are never in another charge. It's just really rare when these few have more than one charge. So I would probably avoid these three on the test. So yeah, let's just skip that one. All right, which formula is not correct? So what's the charge on sodium? It's 1 plus, so there's a total of 2 plus here. So HCO3 has to have 2 negative. HCO3 is 1 negative, so that one's not right. Which one is not correct? So this one's not correct. NO3 is nitrate, and that's 1 negative, and so that's right. HPO4 is 1 negative, and SO3 is 1 negative. No, HPO4. Okay, it's 2 negative. I just said that wrong. And SO3 sulfite is 2 negative. So those are correct. NO3 is 1 negative. I think that's right. So this is wrong because HCO3 is 1 negative, and you've got 2 positive charges there. So they're assuming AG is always +2 here. Let's skip that one. All right, so if the positive is X is 2 plus and the Y is 1 negative, which one of these is correct? That's right. These are still just more practice. I have 4 minutes. Let me look at what else is in this list. Last couple minutes we have. Electron configurations for ions. One, 1,3, 1,3,5, 4s right here. For the oxide ion. So, what's the atomic number for oxygen? 8. So 1, 2, 3, 4, 5, 6, 7. That's neutral oxygen. The reason why oxygen is 2 negative when it's an ion is because these want to be paired, so 2 new electrons come in. That's the electron configuration of oxide. Follow? I guess this wants 1s, 2s, 3s, or whatever. Do you know the answer to this one? Now that I've made this an ion, it has the electronic configuration of it. I mean, it does have the electronic configuration